At this level, when the class gets talking about solid figures, the discussion is almost entirely about classification and calculations based on formulas, rather than the kinds of properties we were looking at when we were talking about things like parallel lines and triangles. So in this lecture, we're going to look at different types of solids, then we'll address the more important formulas in the lectures that come after. So we're going to start off with what are called prisms. Right? To make a prism, you start by taking a polygon, and then you make a copy of it. Right? So we've got two congruent polygons now. Then you line the two of them up, like the upper parallelogram and the lower parallelogram here. Then you connect their vertices sequentially with segments. When you do that, the solid that forms is what we mean by a prism. Right? Now, there's a special kind of prism. This is the kind that we're mostly going to be interested in, called a right prism. Technically, the technical definition is a right prism is a prism where every line perpendicular to one base is also perpendicular to the other base. But in plain English, a right prism is just one that stands upright, like the one in the middle here. And then we've got one more special case. A right prism where all the sides are congruent is what we call a cube. So if we take a prism and we shrink one of the bases down to a single point, that's what we mean by a pyramid. And if you take that pyramid and you change its base from a polygon to a circle, then you get what we call a cone. And if you go back to that prism and make both of the bases circles, then you get what we call a cylinder. And again, I've got examples of those here. And these are all what we would call right pyramids, right cones, and right cylinders. Again, because just in simple English, they all stand upright. The definition would be the same for a cylinder as for a prism. With a pyramid and cone, the way we define it is if you drop a line from the vertex directly to the base, it's perpendicular to it. All right, so finally, our last shape here, the only one that doesn't have some kind of flat surface on it somewhere, is a sphere. And I've got the definition here, and I put the definition specifically for this one because I wanted you to compare it to the definition of a circle. Remember, the definition of a circle was the set of all points in a plane that are equidistant from a fixed point. Well, if we just remove those three words, in a plane, then we get the definition of a sphere. Because now we've stepped up from 2 dimensions up to 3. So before we move on and start talking about area and volume of these things, I wanted to stop and take a look at this formula because it's one of my all-time favorite mathematical formulas. If you go online and you search for list of most beautiful mathematical formulas, yes, there really are such lists. This always is going to show up on it. Right? And it's called Euler's formula. It goes back to a very famous mathematician named Leonhard Euler. And what this says is if you have what's called a polyhedron is just a three-dimensional figure whose sides are all polygons. So, if like all the ones I've got here in the slide, if you look at any polyhedron and you add up the number of vertices and you subtract the number of edges and you add the number of faces, you're always going to add up with 2. Doesn't matter how big it is, doesn't matter how small it is, how simple, how complicated, always going to equal 2. So let's test this out on some of these shapes here. If you look at this one on the left, this slanted prism, there are 8 vertices, 4 on top, 4 on the bottom. There are 4 edges in the top base, 4 edges in the bottom base, 4 more around the outside, so that's 12. And faces, there's the 2 bases on the top, there's a base on the top, base on the bottom, that's 2. 4 more around the outside, that's 6. 8 minus 12 plus 6 is 2. I'll let you do the middle one here in the middle yourself if you want to try it out. Let's take a look at this one on the far right-hand side, because that's the one where things got a little complicated. And you'll see it's still not going to make a difference. If we count up the vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's it. I think I caught all of them. I didn't miss anybody. Okay, vertices, there are 9. Edges, there's 1, 2, 3, 4. That's that left-hand uh, quadrilateral. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think I got them all. And how many faces are there? Let me clean this up. There's 1, 2, 3, 4. Let's see if I missed. Friend, I'm going to miscount. I'm going to do that again. There's this one. That's 1, 2, 3, 4, 5, 6, plus the bottom and the top. So that's going to be 8. So now if we do v minus e plus f, 9 minus 15 plus 8, look at that, came out to 2. So if you're looking for some shapes that you can try this out with your students. There's thing people do called role-playing games, maybe for Dungeons and Dragons. They use a selection of dice in those games. They use a 4-sided, 6-sided, 8-sided, 10, 12, and 20-sided. Right? You can find these for sale online. Those are all polyhedron. Right? So you can buy a couple sets of those, hand them out to your students, and they'll have these actual physical polyhedron they can hold in their hands to test out this formula with. So now that we have several different kinds of solid figures to talk about, in the next lecture, we're going to take a look at different formulas that we can use to calculate the area of the exterior of these figures.